Welcome to EE301 Lesson 31, where we're going to learn about Wye-Delta three-phase circuits. Before we jump into this new topic, let's review what we already learned about three-phase circuits, which are of the YY type. Now, YY circuits would be something like this, which we can distinguish by the fact that in this circuit, I have a neutral both at the source and at the load side. Our technique for solving this YY circuit was to actually use a single phase equivalent that represented one of the three phases in the circuit. Single phase equivalent is easier to solve because it's a simple series circuit. One distinguishing feature about the single phase equivalent is that we always draw a short between the two neutral points. And this is because those two neutral points will have the same voltage when the system is balanced. And this is true regardless of whether or not there is a cable connecting the two neutrals. In this lesson, we're going to cover Wye-Delta circuits, which are like the circuit at the bottom. Wye-Delta circuits have a Y-connected source, which we can see from the neutral here, but they have a delta-connected load. Delta loads are distinguished by the fact that they have no neutral point. This poses a problem for our use of the YY equivalent because there is no neutral. And the single phase equivalent always includes the same terminals, so these neutral points are very important to have. In this lesson, we're going to learn how we can still use the single phase equivalent circuit for Wye-Delta systems. The key to this is to transform your delta load into a Y equivalent load. This Y equivalent load, where each leg has an impedance of ZY, must have an impedance that is equal to the original Z delta divided by 3. Because this Y equivalent load still has a neutral point, we can use the single phase equivalent that made solving YY circuits so easy. Remember that the single phase equivalent model is limited and that it cannot represent things that are not in the model. In order to talk about things that are not represented in the single phase model, such as VAB and IAB, we're going to need to know some conversion factors for delta. So let's relook at the phase quantity versus line quantity relationship for delta connected components. In the last lesson, we introduced the difference between phase quantities and line quantities for the Y system. Now we're going to do the same thing for the delta systems. Remember that phase quantities are defined as either the voltage across or current through one phase element. For example, if I look at this delta connected component at the right, and I look at one phase element, a voltage across that element happens to be VAB. That is, it's from node A to node B. We could look at the phase current as the current through that leg, which is a current we haven't discussed before, and that is IAB. It is the phase current because it flows through one leg. Remember that line quantities are defined differently than phase quantities, but not exclusive of them. The line voltage, or the line-to-line voltage, is the voltage between phase terminals. For example, between the terminals A and B, I have VAB. That is, by definition, a line voltage or line-to-line voltage. The line current is the current passing through a phase terminal. That is, for example, IA, it enters terminal A, so by definition is a line current. Another line current would be IB because it enters terminal B. If you recall from the last lesson on Y components, there was a conversion factor that was required for voltage, but the currents were identical. We actually have the opposite relationship here with the delta connected component. If we look at the phase voltage for a delta component, we already stated that this was, for example, VAB, because it was across one leg. If we look closely, this also happens to be the associated line voltage, which is also called VAB. This is because a delta-connected component is connected directly to the terminals end-to-end. Therefore, we have that VAB equals VAB. That is to say that for delta components, V phase is equal to V line. However, if we compare the phase currents with the line currents, we find a very different relationship in the delta. In delta, the phase current is IAB. But if we consider what happens at node A, we must acknowledge that there is a KCL relationship or current splitting between the different currents, specifically between IA, IAB, and ICA. I could write the KCL equation as IAB equals IA plus ICA. If I know that IAB and ICA are identical except for 120 degrees apart, then by definition I know IA cannot equal IAB. Therefore, we come to the result that the phase current, IAB, does not equal the line current, IA. In fact, they're going to be related by a conversion factor. What we see now is that we have an opposite requirement for a conversion factor than we had for the Y component. So we have a different phase to line quantity relationship. To deduce the conversion factor between the phase current, IAB, and its associated line current, IA, let's perform KCL at the node where they meet. We obtain the KCL equation at A, that is, IAB equals IA plus ICA. I could rearrange that equation to solve for IA, and obtain that IA equals IAB minus ICA. Now notice that the terms on the right here are both phase currents. If I arbitrarily take one of those phase currents to be at 0 degrees, I know the other one's shifted by 120 degrees. If I were to plot those phasors out on the real imaginary plane, and arbitrarily take IAB as the reference phasor, then performing IAB minus ICA yields a line current IA, like so. If we observe IA is greater than IAB by a certain factor, and that it lags by 30 degrees. This is how we derived that the conversion factor between the line current and the phase current is that the line current is larger by a factor of square root of 3, and that it will lag by 30 degrees. Mathematically, this means that we multiply the phase current by square root of 3 angle minus 30 degrees. Notice that this is different than the voltage conversion factor for Y, which used an angle of plus 30 degrees. Also, in contrast with Y, the delta connected component has an identical relationship between the line voltage and the phase voltage. So no conversion factor is necessary for the voltages. Now that we've discussed the phase and line quantities for a delta-connected system, we can actually start talking about the Delta-to-Wye Transform. We already previewed that this transformation was key for us to be able to solve Wye-Delta systems efficiently. The key to this technique is that if I have a balanced delta load that has an impedance in each leg of Z delta that are all the same, then I can convert that delta load into a Y load, according to the transformation factor that each of the impedances in the Y have to equal a certain ZY. And the rule for this equation is that ZY equals Z delta divided by 3. This is the key equation that allows us to get from the delta impedance to the Y impedance and obtain the key neutral that's required to solve with a single phase equivalent. Let's recap our strategy for solving Wye-Delta problems. We're going to take a Wye-Delta circuit and convert it to a YY circuit using a ZY to Z delta conversion. That means that ZY equals Z delta divided by 3. Once you have that YY equivalent model, you use a single phase equivalent model where you draw a short between the neutrals and you solve on that single phase equivalent model and extrapolate it back to the original three-phase model. Now, because the original Wye-Delta system includes terms that cannot be solved for in the single phase equivalent model, such as VAB and IAB, you must use conversion factors to obtain them. Remember, IAB equals IA divided by root 3 angle minus 30 degrees. VAB could be obtained by Ohm's law, where VAB equals IAB times Z delta. Notice that I use Z delta in this formulation because that is the impedance that IAB actually flows through. And that solves Ohm's law for VAB. To obtain anything that's not in the A phase, for example, IB, all you need to do is use the phase sequence information. That means you shift the values obtained for the A phase by plus or minus 120 degrees. In this practice problem, I'm asked to analyze a Wye-Delta circuit. I can see that it's Wye-Delta because I have a neutral on the source side, but I have no neutral on the load side. I'm told that the load impedance, that each of those legs, is equal to Z delta, where Z delta is 2 minus J3 ohms. I'm also told that the source, VAN, is equal to 440 angle 0 degrees volts RMS. The technique here is to use a single-phase equivalent circuit, but to do so, I must first convert this delta load into a Y load. In this Y load, each of the impedance legs, ZY, has got to be equal to Z delta divided by 3. In this case, that comes out to 2 minus J3 ohms divided by 3. That equals 2/3 minus J1 ohm. Now that I have an equivalent Y load that has a neutral point, I'm ready to use a single-phase equivalent model of the circuit. The single-phase equivalent model always looks the same. It always starts with a voltage source that is between the terminals capital A and capital N. That voltage source is always going to be V capital A capital N. Between capital A and lowercase a, I draw any line impedance that may exist. In this case, there is none, so I draw a short. Between lowercase a and lowercase n, I'm always going to draw ZY. In this case, that's the ZY that I just calculated. So I write 2/3 minus J 1 ohms. In a single-phase equivalent, I always draw a short between the two neutral points because those neutrals are going to have the same voltage. In this problem, I was given VAN directly, so I know that it is 440 angles 0 degrees volts RMS. Now that I've built every component in my single-phase equivalent model, I'm ready to start solving for the line current. This is almost always the first thing you should do in the single-phase equivalent model. It's also a good idea in this problem because I was specifically asked about this line current. To solve for IA, I rely on the single-phase analysis techniques that we've already learned in the course. In this case, I apply Ohm's law, where IA is going to be equal to VAN divided by ZY. That comes out to 440 angles 0 degrees volts RMS divided by 2/3 minus J 1 ohms. It comes out to 366.1 angle 56.3 degrees amps RMS. I'm also asked in this problem about the load side line voltage V lowercase ab. This also happens to be the phase voltage for a delta connected load. If I look for VAB in the single-phase equivalent circuit, I can't find it because there is no B. To find VAB, I need to use a conversion factor. Remember that I can find IAB, the phase current, from IA by the conversion factor where IAB equals IA divided by square root of 3 angle minus 30 degrees. Some numbers, that means that IAB is equal to the 366.1 angle 56.3 degrees amps RMS divided by that root 3 angle minus 30 degrees. That obtains a phase current of 211.37 angle 86.31 degrees amps RMS. Once I know IAB, I can obtain VAB through Ohm's law, where VAB is IAB times Z delta. Notice that I use Z delta here because that is what IAB actually flows through. There's no IAB in the single-phase equivalent circuit, and there's no IAB drawing where I have it flowing through a ZY. Numbers, that's the 211.37 angle 86.31 degrees amps RMS times my Z delta 2 minus J3 ohms. This obtains the final answer of 762.1 angle 30 degrees volts RMS. In this practice problem, I again have a Wye-Delta system because I have a neutral on the source side and I do not have one on the load side. In this problem, I'm told the source side line-to-line voltage V capital AB. That is equal to 240 angle 0 degrees volts RMS. Notice that this is not going to be the same as V lowercase ab because there is a line impedance in this problem. Z line equals 3 plus J2 ohms. And this is the same for each one of the lines shown. I'm also told that Z delta, that is each leg of this delta component, is equal to 21 plus J9 ohms. I'm told that the source is an ABC sequence. And then I'm asked to calculate the line currents and the load side phase voltages. Remember that load side phase voltages are the voltages across each of these legs, so VAB, VBC, and VCA. For a delta-connected load, those are identical to the line voltages at the load side. Again, the recommended technique is to convert to a YY and then to a single-phase equivalent circuit. To convert my delta load to a YY, I simply need to take that ZY is equal to Z delta divided by 3. That obtains 21 plus J9 divided by 3 equals 7 plus J3 ohms. That's my equivalent Y impedance. Now that I have my equivalent Y impedance, I have a neutral, and I can build the single-phase equivalent model. Single-phase equivalent model includes the voltage source, V capital AN, between the capital terminals A and the capital terminal N. It includes a line impedance, if there is one, between the capital A and the lowercase a. In this case, there is a line impedance, so I'm going to put in 3 plus J2 ohms. You can pull this directly from the three-phase drawing. Between lowercase a and lowercase n, I'm always going to draw zy, and that's going to be the zy that I just calculated, the 7 plus J3 ohms. Between the lowercase n and the capital N, I always draw short. Now in this problem, I was not given VAN directly, I was given V capital AB. To complete the single-phase equivalent for this problem, I need to use a conversion factor. Remember that for a Y-connected component, such as the source here, I can use the conversion that V capital AB equals V capital AN times square root of 3 angle 30 degrees. If I rearrange to solve for V capital AN, I find that V capital AN is V capital AB divided by root 3 angle 30 degrees. With numbers, that's 240 angle 0 degrees volts RMS divided by that root 3 angle 30 degrees, which yields 138.56 angle minus 30 degrees volts RMS. That's my value of the voltage source here. Now that I have every component in my single-phase equivalent model, the first thing to do is to solve for the line current IA. I use Ohm's law to solve for IA, or in this case IA is going to be equal to the source voltage, V capital AN, divided by the total impedance of my single-phase equivalent. That's my Z line plus ZY. With some numbers, that's my 138.56 angle minus 30 degrees volts RMS, divided by 3 plus J2 plus 7 plus J3 ohms. That yields 12.4 angle minus 56.6 degrees amps RMS. Now because I'm asked for all of the line currents, I also need to know what is IB and what is IC. We know that because this is a balanced circuit, they're going to have the same magnitudes as IA. So I can immediately write that they're going to be 12.4 amps RMS in magnitude. However, for the phases, I need to know the phase sequence. Since this is an ABC sequence, I know that B comes second. We always know that the second phase is always going to have a phase that is 120 degrees after phase A. So it's going to be phase A minus 120 degrees. In this case, that's the minus 56.6 degrees minus 120 degrees. That gets me minus 176.6 degrees amps RMS. For IC, I applied the plus 120 degrees to minus 56.6 degrees, and I obtain 63.4 degrees amps RMS. I'm asked about the load side phase voltages, and remember that phase voltages are those voltages across one element in the load. In this case, for example, it would be a VAB on the A phase. Because VAB does not exist in the single-phase equivalent, I need to again use a conversion factor. To obtain VAB, I can use Ohm's law with IAB. I can obtain IAB from IA using a conversion factor. Remember that IA is equal to IAB times square root of 3 angle minus 30 degrees. Notice that this conversion rule for delta has a minus 30 degrees, whereas the conversion rule for Y had a plus 30 degrees. If I rearrange to solve for IAB, IAB is equal to IA divided by root 3 angle minus 30 degrees. That's 12.4 angle minus 56.6 degrees amps RMS divided by my root 3 angle minus 30 degrees. This yields that IAB is equal to 7.16 angle minus 26.6 degrees amps RMS. If I then apply Ohm's law for VAB, I obtain that VAB has to equal IAB times Z delta. Again, remember whenever I use Ohm's law with IAB, I must be using Z delta because that's the impedance that IAB flows through. With some numbers, that's my 7.16 angle minus 26.6 degrees amps RMS times the original Z delta load, which is 21 plus J9 ohms. That obtains a voltage of 163.5 angle minus 3.37 degrees volts RMS. Because I'm asked about the other load side phase voltages, that is VBC and VCA, I need to use the phase sequence information to help me complete that. I know that they're going to have the same magnitude, so I can immediately write 163.5 volts RMS. However, for the phases, I need to apply the phase shifts, so I apply minus 120 degrees to the BC phase because B comes second in ABC sequence. That yields minus 123.37 degrees volts RMS. For the VCA phase, I add 120 degrees, and that yields 116.63 degrees volts RMS.